Experiment 6 discussion. So, in terms of logistics, since this is our first interaction on a large scale after several weeks, let me talk to you guys about the things that we need to be on the same page on. So let's see. If I go to the class homepage, the Piazza page, I hope you guys can see that there have been several documents attached. So there is a document on the changes that are going to happen for this class, and if you click on that, I have updated it with the current information. So everything that is highlighted has been updated. So please review this document carefully and in detail. The undergraduate student assistants are going to be holding WebEx office hours various times during the week, and the time that they are going to start doing this is also mentioned. Please take a note of that. And there is a WebEx protocol that I have laid out. Hopefully, everybody sort of follows that. It'll help me and you to so that things can go smoothly. So I would encourage you guys to turn off your mics and camera uh, and uh, type in your questions with a serial number. So that will help me to figure out who asked the question first. The class website has been updated. So if you look at the calendar for our class, all the things have been updated in that the due dates are current. So experiment 6 due is Thursday of the following week. Experiment 7 is due the Thursday after that. Project 3 is the Thursday after that. And then the Monday of the last week of classes, we have experiment 8 due. And as you can see, there's no project 4 or project 2 that is due. So make a note of that. One more thing that I would like to clarify: I'm no longer going to take attendance, so you do not need to watch the class videos and answer the um, daily questions. Everybody gets attendance for the rest of the semester. Now, what I've been doing so far in terms of YouTube videos. So far, we have a video on the class walkthrough, and today morning I had section 1 class from 8 to 10. I recorded that and I posted that on YouTube. So if some of you prefer watching or rewatching the videos, you have that option as well. I'm going to do the same thing with this particular section. So all of this is recorded. Okay, so I think that's about it in terms of logistics. Um, yes, project 4 is removed. Yes. If there are logistical questions, you guys need to let me know soon. Otherwise, we can start talking about experiment 6. I'm going to minimize this. I'm going to go to experiment 6. Do we still get the parts assigned for experiments? That's a good question. No, we are not going to get the parts assigned for experiments. Uh, that aspect of EI is no longer going to hold true. Um, so, no signatures. You just work on the experiments and projects and submit them on Gradescope without the signature. So, you don't submit the signature page. If I can just uh, remind the people who are joining right now, please turn off your camera so that we can use the available bandwidth efficiently. Turn off microphone and camera, please. Uh-huh. All right, so let's go ahead and get started. If Are we expected to submit the upcoming assignments with our partners? Yes, I'm expecting that you submit the assignments with your partners. However, if there are any issues regarding your partner or partners, you guys need to email me privately and then we can discuss a solution. But yes, the logistics in terms of experiment partners and project partners is going to work the same way. Other questions? Okay, let's get to it then. So in experiment 6, we are focusing on electronic switching. So the goal is to essentially convert an analog signal which takes in an analog input. Analog input essentially means that the signal, whether it be a voltage signal or a current signal or any sort of signal, has values on a continuum. So there are values that are continuous in terms of amplitude, and there are values that are on a continuum with respect to time. Uh, all right, let's continue with the question here. What if the people who have the parts kit don't have the analog discovery? How are we to build the circuits and test them? Uh, I have already built the circuit and I have tested the circuit and I have uploaded the results on Piazza. That is referring to item number 1 on the new logistics for the class. So let me pull that window up again quickly. So the changes for this class, the first point is this. Because students are in different parts of the world right now, most of them do not have access to the parts or the analog discovery. I'm going to be building the circuits. I will show you how to build them, and I will show you how I measure the inputs and outputs, and I will share the results on Piazza. In fact, I already did. So if you go under resources on Piazza page, you will find all the plots that I generated this morning. Okay, I hope I answered that question. Coming back to our discussion on switching. So we have an analog signal here which has all the values in amplitude and it is defined on a time continuum, but I might not need all the values. Right. So, for example, if you had to do a temperature measurement of your room, you would not be interested in knowing that the temperature is right now 73.14 Fahrenheit and 73.13 Fahrenheit. You would not need to make a very, very precise measurement all the time. You may be interested in knowing it maybe every once 5 minutes, 10 minutes, and some sort of approximation might be okay. Which means that we are going to need some way to convert an analog signal into a binary signal, something that has discrete levels. So something like a staircase signal, which has discrete levels, or even something. So to get to this place, we need something that can give us high and low levels to begin with. So that's what we are going to call as a binary signal, something that has only two states, on, off, low, high, um, hot, cold, only two levels. So in this experiment, we are going to learn how we can switch electronically from that low to high, high to low state, depending on a given uh, analog signal, a continuous signal. So that's what experiment 6 is about. And to help with this, we are going to need op amps and we are going to also need transistors. Op amps, you guys have seen them in experiment 4, 5, and project 2, but you have not seen transistors yet. So we are going to spend some amount of time today talking about what is a transistor, what do we use it for, and some transistor related analysis. Let's move on to the next page. So before I start talking about the electrical characteristics of a transistor, let's talk about a real world example of how you can think about transistor operation. So let's see, real world operation, real world example, right? The way I like to think about transistors is by imagining a door. And let's say you have a lot of people outside the door who want to get in to a room. And you are waiting at the door, and you essentially have the control to either allow people to go in or stop people from going in. So essentially, if you open the door and you are the one who is controlling this, right? So you are basically in charge of this operation. So if you open the door, people can go into the room. And if you close the door, people are not allowed to go through the room, to go enter the room. So this is exactly how a transistor works, switches between the on and off state, as in the door being closed or open, at least in the simplest terms of two states. The transistor actually has three different regions. We are talking about the two extreme regions with this particular example. So now, having discussed a real world example here, let's get into what a transistor is. Well, clearly, you need three terminals. What are those three terminals? Well, you have a base, you have emitter, you have a collector. Why is this called an emitter? It's called an emitter because this is where this terminal is what emits the electrons, and collector is what collects the electrons. So the flow of electron is going to go from pin number 1 to pin number 3. However, the direction of conventional current is going to go from 3 to 1. So the current flows this way from collector to emitter. However, the direction of electrons is exactly the opposite way. Now, what is the base? Well, the base is you. Why? Because you are the one opening or closing the door. So the base voltage at the base with respect to the emitter terminal, let's call it VBE, is in control. So you can either open this door or close this door by controlling this voltage, VBE. That's between pin number 2 over here, or the base terminal, and the emitter terminal. So think of emitter as the people and think of collector as the room. So people want to enter the room, but you are there right in the middle controlling the door. Let's see. How do I know which pin is what? Well, the transistor looks like this in your parts kit if you have one. Otherwise, I'll show you one later today. And if you are facing the flat side, then the leftmost pin is pin number 1, which in this case is the emitter, and the rightmost pin is the collector. So that's how we know the orientation of these three pins, and that's how we attach that real world example to those three terminals of the transistor. So let's see what that opening of the door and closing of the door means in terms of the transistor. When VBE, the voltage at the base with respect to emitter, is less than 0.7 volts, it's very small. In that case, transistor, let me call this transistor Q1. Q is the letter typically used for transistor, like R1, R2, R3. For transistors, it's going to be Q1, Q2, Q3. So Q1 is going to be off. If voltage at the base with respect to emitter is less than 0.7 volts. So 0.7 volts is sort of a limiting voltage here, typically for all the BJT transistors of this type, PN2222. Q1 is off. What does that mean in terms of our real world example? That means the door is closed. Nobody can enter. Door is closed. The other extreme is VBE is greater than 0.7 volts, Q1 is on, and that means door is open, which means current can flow through the transistor. So just a quick note here, if you guys need to take a quick break, you can do that. Also note that these videos are recorded and they are posted on YouTube. So if you miss a couple of minutes, you can always go back and watch that missed part of the lecture. Okay. Let's see. There's a question here. Let's. Do we still need to watch the online lecture videos? Yes, Corey. Absolutely yes. Those lecture videos are going to give you the in-depth background. I am giving you some background, but I'm not going too deep. So you still need to watch those lecture videos. If I was, because they are pretty long, so I would recommend that you spread them over a week time, and not watch it at once, all at once. Okay, so coming back to this. So those are our two cases. VB is less than 0.7, VB is greater than 0.7. So what would happen if it is less than 0.7? Well, if it is less than 0.7, then the door is closed, meaning no current can go between collector and emitter. So you would essentially draw, so instead of this, you would essentially draw an open circuit. This is your collector, this is your emitter. You would draw an open circuit when VBE is less than 0.7 volts. And on the other side, you have when VBE is greater than 0.7 volts, you have got a short circuit because you're allowing all the current to pass through the transistor. So between the terminals, collector and emitter, people into the room. So those are our two extreme cases, and they have names. Their names are cutoff region for VBE less than 0.7 volts and saturation region for VBE greater than 0.7 volts. I said there are three regions. So the third one is actually called the active region. The active region is when the transistor functions as a current amplifier. So it's between the on and off state, and during that transition, very close to around 0.7, it functions as a current amplifier. So if I denote this current that flows from collector to emitter as ICE, and if I say the current that flows into the base as IB, then during this active region, ICE will be about 170 times IB. This is called the current gain factor, which is denoted usually by the letter beta, current gain. So that's what happens in the active region. So we have got transistor off, transistor on, and the active region, so a current amplifier. So that's a quick discussion on the three regions of a transistor and sort of a general discussion on base emitter collector, and relating that to a real world example. All right. That 0.7 volts is going to be our voltage of interest to monitor whenever we look at this sort of a transistor. Three terminal device. Uh, Next, with that, let us try to analyze these two circuits here. And in the first one, let's try to answer what is IB, so the current that flows into the base, right here. And we will also try to answer what is the current that flows from collector to emitter, ICE. How much is that going to be? So with this example, let's try to answer these two questions. Now, the first thing that we would need to find out here is whether Q1 is on or off. Well, that depends on how much voltage are you applying at the base with respect to the emitter. Over here, we are applying V in as 1 volt. I need 0.7 to turn this on. So the 0.7 volts is going to be required to turn the Q1 on. And because we are supplying more than that, it is going to be on. And it is DC. So it's not changing with time, which means that the transistor is not switching in this particular configuration because this is 1 volt constant. But it is going to be on because this is greater than 0.7. But we are still left with 0.3 volts because if we give it 1 and we are using up 0.7 to turn on the transistor, we are still left with 0.3, which goes across the only element that is left, which is R1 in this case. So with this particular voltage, I can actually calculate IB. So IB is essentially going to be the voltage across R1 divided by the value of R1 should equal 0.3 milliamps. So that's the amount of current that flows through R1, which is the same as current that flows into the base terminal of the transistor Q1. So that's step number 1. Step number 2, because Q1 was on, we had to replace Q1 with a short circuit between the collector and emitter. So let me just draw a straight line over here. Right now it's on, so it's allowing all the current to go through. Question is how much current is going through. So if that is a short circuit, that means that this is a closed loop. And in this particular loop, we have a voltage source, we have a 1 kilo ohm resistor and ground. That's it. So that will allow us to calculate what ICE is going to be. ICE is going to be 9 volts divided by 1 kilo ohm. It's going to be 9 milliamps. Now, as you can see, there is already a gain, but it is not as high as it would be if you were operating very, very close to 0.7 volts. All right. So that's circuit number 1, and that's how you would analyze it. Now let's move to circuit number 2 over here. Is it always 0.7 volts? Yes, sir. It is always 0.7 volts. Next, we have another circuit. Let's quickly do this. Question 1, is Q1 on? Yes, it is on because we are providing more than 0.7 at the input side to the base terminal. So this will be on, which means that there will be a, this is going to be your circuit. Now the question is, why did I ignore R3 in this case? I ignored R3 because it has a 1 kilo ohm resistor and it is parallel to a short circuit. So if electrons have the option of flowing through short circuit or a resistor, they are going to take the path of least resistance. And R3 is going to be neglected. So it's almost as if R3 is not even connected. Now, I know that Q1 is on. Let's try to find out what is R3. What is IR3 going to be in this case? IR3 is going to be 0 amps in this case because no current flows through R3 when the transistor is on. IR1 or IB will be the same as earlier, so still 0.3 milliamps. The reason is this is still 0.7 volts to turn on, this is still 0.3 volts, so the current through R1 remains the same, so it's still 0.3 milliamps here. Another interesting question we can answer with this is here. So let's assume that Q1 is off. We already know that it is not, but let's just assume for the sake of this calculation. If Q1 were off, maybe this is 0.5 volts. If this is 0.5 volts, then Q1 is off. And if Q1 is off, what would be the current through R3? In that case, my circuit would slightly be different. Because this is off, it's an open circuit there. So this point is absolutely not connected to that point. That's an open circuit, which means my loop is going to be this way. So now IR3 is going to be different. IR3 is going to be, we are offering a 2 kilo ohm resistance to a 9 volt battery. So it should be 4.5 milliamps. Only when we assume that Q1 is off. But we know that our answer for this, the correct answer for this is 0 amps because Q1 is on. Okay, so I hope that these two examples are helping you get comfortable with transistor related circuits. Okay, let's move on here. Simulation, simulation, simulation. The next thing on the agenda is two very important things: comparators and Schmitt triggers. These two are op-amp based configurations that help us convert that analog signal into a binary signal. One is better than the other, and we are going to see which one turns out to be better. And let's do that analysis on a separate worksheet here. So I have taken up a op-amp based circuit and I have pasted it on this particular paper. I have got figure B1 from our experiment over here, an op-amp that has a non-inverting input on pin number 3, an inverting input on pin number 2. The inverting input is connected to ground. We are using +5 and -5 volts DC supplies as our saturating voltages on the high and the low side. And pin number 6 is giving us the output, which we have connected to a 1 kilo ohm load resistor. And pin 3 is connected to an input signal that is changing with time. So it's AC signal, it's changing with time. Pin number 2 is constant, 0. So this is actually a comparator configuration. What are you trying to compare? You're trying to compare the two input signals that are present at pin number 3 and 2, meaning the non-inverting input and the inverting input. So in this particular configuration though, it is going to be 0 volts, and we are comparing an input signal, input voltage signal, to 0 volts. That's what we are doing. And let's see, and we are calling that a comparator because it's a simple comparison. Input signal compared to 0 volts. That's it. Our reference voltage here, or the threshold voltage here, is 0 volts. Why is that 0 volts? Because I'm comparing the input to whatever I connect to pin number 2. So that's 0 volts. What is the configuration? The configuration is non-inverting because the input is connected to the non-inverting terminal of the op amp. So it's a non-inverting comparator. Now let's see how this compares the input. So to do that, we are going to write two statements as the analysis statements. So let's see. Input signal, it's a sinus, it's a changing with time, right? So the input signal could be doing this. And we are comparing this analog signal with 0 volts. So the analysis, the two statements that I need for this analysis are Vin could be greater than 0 volts, my comparison voltage, or Vin could be less than 0 volts. If Vin is greater than 0 volts, then my output is going to be plus 5 volts. And when Vin is less than 0.0 volts, my output is going to be negative 5 volts. Now, two questions arise based on these two statements. One is, how do we know it's plus 5 and not plus 6? Well, because we have connected it to a plus 5 volt supply and a negative 5 volt supply. So that's why those two voltages are plus and minus 5. The next thing is, how do you know that if the input is bigger, the output is bigger, and the input is smaller, the output is smaller? Well, I know that because the configuration is non-inverting. If it were an inverting comparator, then these two would be switched. So when Vin is greater than 0, V out goes negative 5, and so on. So that's how I know that these two statements are going to be okay. So using these two, I can sketch things. So those two are crucial here. So what am I doing? I have drawn an arbitrary input waveform. Let's see. So a comparator acts as a switch between two voltage sources. Yes. Next, so I've taken an arbitrary input waveform, Vin, and it's an analog waveform. My x-axis is time, my y-axis is a voltage scale, and my goal is to sketch V out based on these two statements. So because my threshold is 0, let me just highlight that threshold or the reference voltage. It is going to be very easy for me to sketch the output. As you can see, to begin with, input is greater than 0, so it's going to saturate plus 5 until here, and then it's going to go negative 5 there, stay there until that happens, then jump up, do that, jump down, go up a little bit more, jump down. So I am essentially comparing the input with 0 volts, and I am going up and down when the input goes up and down compared to 0, which is my threshold here. And stays, goes down. It is in phase with my input, and I have a binary signal given analog signal. So that's going to be my output. Let me just quickly say that V out. So my input was going up and down. Sorry, it was analog waveform. My output is now a digital signal, goes between only +5 and -5. With standard TTL conventions, would the negative voltage supply of the op amp uh, just be grounded? Uh, so we are using uh, CMOS gates. We are not using TTL. So it's not going to be grounded for our case. We have, all right, so there are some key things that are happening over here. One is, if you look at this aspect of the input signal, it looks like it was meant to go high and it was meant to go low over here. However, there's a problem over here, as you might be able to see. If you look at the input in this region, that could be noise. How do I know it could be noise? Well, noise is something that will have zero mean and a small value, but it will be a zero mean signal. And that blue thing right in the middle over there, that is sort of doing the same thing. Even though they are small voltages, they are going up and down close to zero at a very high frequency. So that could, this comparator is reacting to that noise. So that's a problem. The problem with a comparator is that it reacts to noise. The noise might be very, very small. Even then, because it is going up and down compared to 0 volts, it is going to react to it. That is a problem that we fix with having two thresholds, which is an aspect that we look at using a Schmitt trigger. All right, next. We have another circuit over here, very similar to the one before, but a few changes. The only thing that changed over here is we have added a 1 volt DC supply to the inverting terminal. So now I'm comparing the input with 1 volt instead of comparing it to 0 volts. So what is the configuration? It is still a non-inverting comparator with a reference voltage of 1 volt. And what are the statements for analysis? Well, for the analysis, we have two statements. When V in is greater than 1 volt and when V in is less than 1 volt. When V in is greater than 1 volt, our output is going to be +5, and in the other case is going to be -5 volts, because these two are -5 and +5. And using these two statements, you could essentially draw another sketch like so. All right. Questions about a comparator? All right, let's move forward with a Schmitt trigger. Now, this is sort of the meat of our discussion today. A Schmitt trigger is also based off of an op amp. It is still comparing voltages, but it's slightly different when compared to a comparator. So to do the analysis for this guy, I'm going to need some key voltages. So let's see, I have my input voltage here, V in, and I'm going to call this particular node voltage as V3 because that is 3. Um, R4 and R5 are two additional resistors that were not present in the previous configuration, the previous circuit. I still have the plus and minus 5 voltage supplies driving the op amp saturation voltages. I'm still taking the output on pin number 6 and connecting it to ground using a load resistor of 1K. That's it. So the first thing that we are going to do is talk about what this Vref is. Well, that Vref of 0 volts, that essentially means that this is 0 volts. Because you could have connected a different voltage supply over here. For example, you could have connected a 1 volt DC supply over there. More about that Vref later on, but I just want you to know that that Vref is related to that connection over there. The first thing we are going to do is talk about the configuration. What is the configuration? Is it inverting or non-inverting? Well, clearly the input is connected to pin number 2, which is the inverting terminal. So it's a inverting Schmitt trigger. Next, what is V3 going to be? Because I'm comparing V in and V3. So V in, I know it's an input signal, so that's in my control, but I don't know an expression for V3. I don't even know it numerically. So let me find out what V3 is going to be. That's my goal. That's my next goal. Find out what V3 is. So to do this, let's try an equation. So I want you guys to focus on this particular part of the circuit. And if you see that, you should recognize that V out is essentially being divided between R4 and R5, and V3 is essentially the voltage across R5. So I can write a statement here. V out is divided between R4 and R5. V3 is voltage across R5. So using this, we can analyze this Schmitt trigger. So what is V3 going to be? V3 is going to be V out multiplied by R5 divided by R4 plus R5. And I know V out, depending on the comparison, could either be plus or minus 5 volts. It could either saturate high or low. So those are the two possibilities. So based on this, I can say V3 is going to equal plus and minus 5 volts multiplied by R5, which is 1K, divided by R4 plus R5, which is 1K plus 4K. So this should work out to be plus and minus 1 volt. So if V3 is plus and minus 1 volt, and I'm comparing V3 and V in a inverting configuration, my analysis statements will be such. V in greater than V3, oh sorry, greater than 1 volt plus 1 volt. That implies that my output is going to go low because inverting configuration. Yes, absolutely. V out can be plus or minus 4 volts, and you can change these two voltages to plus and minus 4, and you will get that. Or you may want to take plus and minus 5 from here and use a different circuit that will make it 2 plus and minus 4, plus and minus 4. Any differential results in saturation? Because all right, let's finish this and I'll get to the questions. Assume that we saturate the op amp. If you are saturate, okay. Let's come back to the analysis statements here. V in is greater than plus 1 volt. In that case, V out is going to be negative 5. And when V in is less than negative 1 volt, my V out is going to be plus 5 volt. So I hope you guys see that it is out of phase with respect to the input because of the inverting nature of this Schmitt trigger. We are going to call this an upper threshold, and we'll call this the lower threshold. Upper threshold level, and we have got lower threshold level. So in order for the Schmitt trigger to switch between plus and minus 5, it has to be a big difference, right? Only when you go above the upper threshold or when you go below the lower threshold. So let's see if this is effective and this is able to reject noise. Let's do the same exercise again. So the same input sinusoid, sorry, not sinusoid, AC signal is sketched over here, the same one as before. And because I need the analysis statements, let me quickly write those out. My analysis statements are V in greater than 1 volt, V out is negative 5 volts, V in is less than negative 1, V out is 5 volts. So those are two statements that will help me analyze this. I need, this will help me do this easier. I need a line for plus and minus 1 volt. So let's sketch that. Let's see, 1 volt here, say, and negative 1 volt, say, over here. I'm not drawing this to scale, just to give you an idea about how the output looks. So that's plus 1 volt, and this is, say, minus 1 volt. This is 0. Now, what is the output going to look like in this case? Well, when the input goes above 1 volt over here, my output is going to go down. So before this, it was probably high, and after this, it goes low. And it will jump high only when the input goes below negative 1, the lower threshold. So it will jump there. Next, it will go down again only when the input goes above 1 volt. And next it will switch again over here, and that's it. It doesn't switch after that. So I hope now you can see that first of all it rejected all this noise, right? If this was noise, it has rejected all of that. It didn't react to noise, which is a good thing, right? And it is still able to convert that analog signal to a binary one, plus and minus 5. Okay, so that is initial discussion on Schmitt trigger. We are going to add one more nuance to this. The nuance comes from recognizing that the thresholds on both sides are plus and minus 1. By the way, hysteresis equals upper threshold level minus lower threshold level. So in this case, it is going to be 2 volts. But the thing to note is the thresholds on both sides, positive and negative, are the same, plus and minus 1, or plus and minus 2, and plus and minus 3, and so on. What if we wanted different thresholds on either side? In that case, we would have to change the reference voltage. So in this case, we are going to use a 1 volt supply here at the end of R5, which makes our reference voltage 1 volt, and we can start analyzing this to obtain our new threshold levels. So before we do that, I would like to point out that the voltage over here is of interest to me, the blue point, and also the voltage over here is of interest to me. The voltage over here is going to be V out, because that is V out, and the voltage over here is going to be 1 volt, because that is 1 volt. Now earlier V out was getting divided between R4 and R5. In this case, V out, so let's still call this V3. The first thing that we are going to say is, what is V3? V in is V1, so that's fine, the same as before. However, what is V3? V3 is it the voltage across R5? No, it's not the voltage across R5 right now, because V3 should include the 1 volt supply, because voltages are measured with reference to the ground. So V3 should be written as voltage across R5 plus 1 volt. So let's write that first. So we have got V3 equals VR5 plus 1 volt. The next thing is, what is VR5? If I wanted voltage across R5, I should be doing, what is getting divided? Is V out getting divided between R4 and R5? No, it's not. It's V out minus 1, which is getting divided between R4 and R5. So VR5 is actually V out minus 1. It's divided between R4 and R5, and I'm interested in R5. So I would change the equation simply that way. Next, I recognize that V out could either be plus or minus 5 volts. As before, it can either saturate high or low depending on how the comparison goes. I substitute this over here, I substitute this over here to find out V3. So let's do that quickly now that we have all the necessary steps. VR5 is going to equal plus and minus 5 minus 1 times 1k divided by 1k plus 4k. That should equal 4 divided by 5. So 0.8 volts, or it could be negative 6 divided by 4. So negative 1.2 volts. So those are my two values for VR5. One more step remains, which is V3. V3 equals VR5 plus 1 volt, which means 1.8 or 0.2, negative 0.2. So this would be my upper threshold level, and this is my lower threshold level or voltage. So it changes the response a little bit, but the idea is still the same, to reject that small Gaussian noise. Zero mean the amplitude is small. The So the hysteresis is not quite centered at the reference. Absolutely, yes. Okay, so that's what I have in terms of our discussion on Schmitt trigger and comparator. Um, in terms of symbols, let me point out these two. Actually, let's go back to the experiment and take a look at this particular diagram here. Well, this. This one is probably better. So in terms of logic gates are um, gates that allow conversion or manipulation of logic levels. Logic levels are binary levels, right? So it's high, low, on, off, the kind of binary signals that we have been looking at or trying to derive from an analog signal. So that is a symbol of a NOT gate or an inverter, and this is also a symbol of a NOT gate. The bubble is what signifies the inversion. So if you see a bubble right here and a bubble right there, that is what signifies the inversion of the input. So if a high level goes in, a low level comes out, and that applies over here, or a low level could go in and a high level comes out also here. But the difference is in terms of the symbol is this. There is a hysteresis or the response to two thresholds being shown in the symbol here, which means that this is a Schmitt trigger based inverter. And this one does not have that Schmitt trigger symbol, which means that this is going to be a NOT gate that is based off of a comparator. So those are your symbols. Now, what I am going to do is I'm going to be working on the experiment next. There are very, very few things that are remaining up for discussion for Thursday. Whatever I think of, I will discuss that on Thursday afternoon with you guys. But I think I've covered, in terms of our discussion here, I think I've covered enough for today. I have noticed that part A, B, and C only require simulations, and part D is the only aspect of experiment 6 in which you have to build a circuit. So I'm going to be trying to build a circuit which essentially does this transistor switching on and off, say to turn off and on an LED. So blinking of an LED at a particular speed, which is the experiment that we are going to do next. So this is figure D-4.2 of experiment 6. This is part D. It has voltage source that is that we are going to use analog discovery for, the wave generator from the analog discovery. There is a 7414 chip. 7414 is a 14 pin. This is a 7414 is a 14 pin NOT gate. It has 6 hex inverters. So this little chip over here has 6 NOT gates. We are interested in only using one of them. So we are just going to use pin 1 and pin 2 shown over here, pin 1, pin 2. Note that in order for it to actually invert things, we also need to give it power and ground. So we will still need to give it 5 volts and ground for the IC to be operational, and it will operate on the input to produce an inverted output. The output of this NOT gate, or output of this particular chip, feeds into a 1 kilo ohm resistor that is controlling the base voltage of this transistor. And as this is going up and down, this is going down and up, and this is going on and off. And only when the circuit is complete, the LED over here is going to be either on or off. So if we can see this, let's assume that this is going on, off, right? In that case, the point B is going off, on, and point C is going to connect to ground if Q1 is on, and a dangling wire if Q1 is off. So that will either turn on the LED or turn off the LED. So that's how. So if Q1 is on, what is going to happen? Q1 is on. Is the LED on or off? Well, if Q1 is on, that means there's a short circuit there, which means LED is on, and vice versa. If Q1 is off, then point C is a dangling wire and the circuit is not complete, which means no current flows and the LED does not have enough voltage to turn it on. Red LEDs usually require about 1.5 volts to turn them on. We are giving it a lot more than that, 5 volts. So the remaining voltage will go across R2. More about diodes and LEDs in experiment 8. What we can do right now is set up the experiment and go through it. So what I'll do is this. I will need to change my view in order for us to start working on the experiment. I need to make a few changes, and we also need to probably take a quick 10-minute break. So it is right now 5:07. Let us take a short break of 10 minutes. Let's say 5:20. Let's come back over here at 5:20. So back at 5:20. That's Eastern Daylight Saving Time. When the magnitude of V out cannot be smaller than. I will still have this meeting open while I make those changes. You might see some things going in and out of view, but we will come back in a few. Let me stop the recording.